So before we start, few logistic things. For office hours, we're gonna move them Monday and Wednesdays because you guys requested it. So let's see, I have an email somewhere. I think it's at 2 p.m. Snell Library, room 43. But let me make absolutely sure that it is the case. (2 p.m. room 043). Monday, Wednesday, 4 p.m. Snell Library, 043. The other one stays the same. The Tuesday, Thursday, Friday, right? People said it's better in the afternoon. I talked to the TAs, they'll figure it out. Homework 3, we need teams of 3. How many people are in a team of 3 as of right now? Okay, 1, 2, 3, 4. Does number have to divide by 3, right? How many people in a number? It can be 7, right? It has to be a multiple of 3. So how many people is not in a team of 3?
We are in a team of 4.
Okay, I'd prefer 2 teams of 2 instead of 1 of 4. But come talk to me or email me something and we'll work it out. So for homework 3, which is available as of right now, I'm gonna put probably tomorrow in the afternoon in your Dropbox folder. If I figure out who the team is, X, Y, Z, 3 people in a team, you're gonna get a grand topic, so to speak. By grand topic, I mean something like World War II or Catholic Church or something like that, right? And each one of you will get a bunch of URLs. Some of these might be Google searches, but they're nevertheless URLs. So each people in the team get about 3 or 4 URLs. Some of these URLs are in common to the team. Some of them are not, are per individual. What you have to do is to write a crawler that goes on the web and crawls documents, starting at those URLs I give you. Okay? You can add few of your own. If you say, okay, this is Catholic Church, the topic, and here's a good place to start on Wikipedia, that's okay too. You can take that topic and add few URLs on your own. The crawler is individual. So you can't take somebody else's in your team code to crawl. You have to write your own crawler. But when you put the data together, suppose I'm in a team with them two, we all have 3 URLs or 4 URLs each. One of these URLs is in common, so starting from that URL, we're gonna crawl the same documents, right? If we go by depth or by size, because we start in the same point, presumably we're gonna get the same documents, apart from processing links. Sometimes I'm not gonna follow a link if I think it's a spam, but he in my team might follow that link because the spam analyzer or processing might be slightly different. That's okay. When we put those documents together in Elasticsearch, you have to have an Elasticsearch distributed on 3 computers. So I'd suggest get together with your teammates, like soon, and figure out how do we set up Elasticsearch to be, if you set up the same cluster name in a regular network, it will automatically distribute. You can verify this very easily. Set up, if I go hang out with him, he sets up an empty Elasticsearch, and I set up, say, my index for homework 1. If it's communicating properly, he should be able to see my index distributed on his machine. That's by default, the whole shards and replicas and all that, you don't have to worry about it. So Elasticsearch by default has this property. Now, at school, depending on the building and the configuration of the network, this might or might not work. In previous years, most students choose to either do it in somebody's house or they hang out, the 3 people together, or they get together here with a router and they connect their laptops through that router without going through the, say, CCIS network or something like that, just to make it work. we're going to provide at office hours a private network. The TAs will have a router that sets up with a network for this class. And you guys, if you prefer that, can connect to this router instead, so that your Elasticsearch will communicate. But it's, I think, a little bit more messy to do it, other than, you have to come to office hours and do all that. It's up to you. I think some people find out that crawling in advance, like storing those documents, crawl somehow on their laptops, and just do the merging when they get together. It's easier. So they let their computer crawl overnight 50,000 documents, or how many they need to crawl. They store it somehow in Elasticsearch. They store it directly in Elasticsearch private on their computer, but you can store it in however way you want. And then when you get together with your teammates, the merging process, the script that sends data in and out to Elasticsearch, you should verify, every time you send a document to Elasticsearch, you should verify, hey, is that document already in there? Because maybe my teammate already crawled this document, so I don't want to store 3 copies of the same document. It's easy to check, is this document there? If it's there, perhaps keep the most recent version or something like this, right? That process can be done within like minutes, 5 to 7 minutes. Even if each one of you crawl 50,000 documents, to put them together in 3 computers connected in a network, that's extremely fast operation if you do it right. Okay. So I'm saying so now, homework 3 is not available officially until Wednesday or Thursday this week. But you should set up these logistics. Who are my teammates? What kind of computer they have? Can my network talk to their network? Do I need a router? Do I need a hub? Can I do it through the CCIS network or through this network that's available right here? I think people have run into those issues, and we're going to provide this router at office hours, but many people choose to figure out on their own how to do these connections. Okay? As far as I'm aware, Elasticsearch talks by itself. If it's not a network problem, it immediately distributes by itself. You don't need to configure it in any special way. If you just set up the same cluster name, it's going to work. Okay? So homework 3, preparations. Team and Elasticsearch setup. And before I go into indexing, I want to do a quick homework 1 recap issue. Is it working now?
It's working.
So remember when I said no matter how hard I try, somebody's going to do this? And not just him, many people did it. In language models, if a term does not appear in a document, you can just say skip. And the reason, I'm going to explain in a second, I think I said it already twice, this is the 3rd time, is that by saying skip, remember what the score is? Score of a language model generic. It could be Laplace, Jelinek. The score in general for a document is effectively what? It's a sum over the query terms of what? Some logarithm of some probability, logarithm of the probability of that in the document, right? That is, generically speaking, the formula for accumulator, for the score. It's a sum of logs. When I say, in my document D, the query word Virgil does not appear, skip. What value am I effectively using for the whole logarithm if I say skip, don't do anything?
0.
I'm using 0. But logarithm, when the logarithm gives 0, 1. So effectively by saying skip, I'm saying the probability implicit that I'm using to get the 0, it's 1. That's exactly the contrary of what we want. If a term does not appear in a document, whatever the theory is, we don't want to give a high probability, right? This probability value, we want it to be high when the term is dominant in that document, it's like a very prevalent term, and we want it to be low when the term does not appear or appears very rarely or something like that, right? But low for a probability means close to 0. So the logarithm of 0 will be close to minus infinity. So by saying skip or do nothing, I'm actually rewarding the document for not containing that term, because 0 is the maximum possible value per term in this sum. Right? I have 6 query terms, so be a sum of 6 values for each document. Each value will be negative because the logarithm of probability has got to be negative. By putting 0, I'm actually giving the highest possible value for that term in that document where it actually does not appear. It's the contrary of what I want. Okay? Now, the trick with him and others where that skip was not obvious. It's not a for loop. That's obvious, you know, for all the terms, if it doesn't appear, skip. It's not like that. You can create an initial data structure of some kind with some initial values, and then during that process, I'm looking at documents, I'm looking at query terms. There are many ways to effectively skip, but not realize it right away that for a term that not appear in the document, you're actually not changing the value that has been default put there or initialized or something, right? So I think that was his case. I'm not pointing at him because at least 3 other people did the same. Just they didn't come to me, the TAs fixed it. By doing your processing your flow, you should ask yourself, what happens if a query term does not appear in a document? Where in my code I'm doing something about that? What should be the probability be, this probability, if the term does not appear? So say Laplace. Laplace probability for a term that does not appear in a document should be what? TF plus 1 divided by TL plus V. I told you guys have to play with this V because the theoretical V, 11,000 is too high. Maybe it's only 500 or 600 that you need, I don't know. But apart from that, V is a constant. DL is document length. 1 is 1. And because the word does not appear, TF is 0. So the probability would be 1 over this. Let's assume the DL is about 400 and the V is about 1,000. So 1 over 1,400. So the actual value being used in the scoring function would be logarithm of 1 over 1,400. That's not 0. That's actually a small value. Okay? Good. Where are we with homework 2? So how many people indexed the data, including merging? Okay, hands up so I can see them. With merging?
I've done it on a smaller set.
But merging works? Are you sure?
Let's see.
Okay. Right, so we're storing 2 files. That's what I'm going to recap right now, the merging procedure. Every one in our files, it's a hard drive file that is the inverted file, which we cannot read in memory at all times. That's our convention to simulate reality. And there is a catalog file that we always read in memory to help us out where to read and where to write in that inverted file, right? That's what we have. Once you have this procedure for creating those files and merge them, the rest of homework 2 should be pretty much the code from homework 1. Once you get the tier values, DL, whatever else you need, you should be able to run the same code and produce the results list, evaluate to track eval, so on and so forth. Good. So what we have to do today, I'm going to keep writing here, we have to do indexing. We'll spend maybe a few minutes on recapping. Then we have to do encoding and compression. And I think that's enough for today. Well, there was one more thing that I forgot. Somebody asked me. Yes.
I just had a question about homework 2. So, in the last lecture, you talked about the algorithm for finding the smallest window that contains some set of terms, but we didn't really touch on how we're supposed to incorporate that into a scoring mechanism. I mean, like once you have that smallest window, what do you do with it? And also, how do you handle documents that only contain some of the terms, things like that?
Right. Okay. So we can talk about that. I think that's called here. let's talk about two things. That is one. So let's say n-gram, skip gram scoring. And the other one that somebody asked, and I think it's a good thing to mention, is relevance feedback. But there's two versions. So there is a pseudo version and a real version of relevance feedback. The other issue, the meta set issue, how to combine multiple lists, I think we've talked about last time in class. Right. So about the skip gram issue, if you remember, there was a question of if I have 3 words, I get position on all of them, right? I'm looking for the nearest span of those 3 words that appear in my document. The way I showed you that the blurb algorithm, it's out of order. As in, if you think about it, I can put it up, but if you think about it, it looks for the 3 closest numbers. It doesn't pay attention to the order. Is the order of occurrences of those 3 words the same order as in the query? So the skip gram matching is of 2 kinds, in order or out of order. Out of order, it's easier with that algorithm because this out of order, I'm looking for, I have the position lists. Does everybody remember the algorithm from last time? Right? That was a very quick algorithm to find me the closest 3 positions if I have 3 words. Right? So it's doing that. So the blurb algorithm, I think it's blurb finding by Stephen Kenzel or something like that, I don't have his name, produces what? At the end of that algorithm, what do I have? So it was a list of positionings, and then I go through that list in a very efficient way, linear, and at the very end, what do I have? The closest 3 positions. If I have 3 keywords, if I have 5 keywords, I'll have the closest 5 positions. So I have the minimum span. Right? A span is, it starts in position, say, P, and it ends in position P plus Q. Right? So Q is the minimum span, or Q minus 1, depending how you want to count this. Right? So I think his question is primarily, okay, I can get this Q, but there are several issues that I want to touch about. One is, one thing that he didn't mention, multiple occurrences of skip gram. So what I'm mentioning here is in terms of all these methods that you guys did for homework 1, the more the better, right? The more occurrences I have for a unigram or a bigram, the more all these formulas, whether language models or vector space model, they increase when the TF increases. But this algorithm, does this algorithm account for that? By giving me the minimum span, can it produce the same exact value or span for 2 documents, one that contains my skip gram 5 times and another one that contains my skip gram only 1 time? Or, so again, is this algorithm that we talked about last time, finding the minimum span, does it account for the how many times that trigram occurs in my, no. But can I modify this algorithm to count all occurrences? Can I? That would make a good algorithm question for your algorithms class. Here's the list of positioning. That algorithm produces only the minimum span. Instead of the minimum span, I want top 5 spans. Top by top, I mean the smallest ones, right? I want the top 5 spans. So this question formulated this way, is it with the realm of master students algorithms class? We can add a little twist to it and make it like a woo kind of question. I want the top 5 spans in those positions list that do not overlap. So if I'm counting this one as an occurrence, because I see my 3 terms, here's a span, the next occurrence have to start after this one ends to be counted. But of course I have options. I could say instead of counting this and this as 2 long spans, maybe there is a short span that I could get in between them with some out of order positioning. That is a hard question. So if you were into the algorithm mood, perhaps when this term ends, you can think about that. I have this list of positioning, which now is a theoretical question. That doesn't matter if those lists are realistic or not. I have a list of positionings of 3 or 4 or 5 terms, and I want to count to get the top non-overlapping minimum k spans, so k is 5 or 6 or 10. How do I produce that? So that's one issue. This algorithm produces only the shortest span, but it doesn't account for how many such spans can I find. Now, what do you think in terms of unigrams? Obviously, the count matters. For unigrams, there's no notion of matching span. If they match, they match. Matching span starts counting at bigrams, right? Bigrams can be more far away or more close, right? So for unigrams, definitely we think in a quantitative way. The more it appears, the better. How about for bigrams? If I tell you a bigram, let's think about it this way. So I'm talking about this issue now. On this end, I'm talking about quantitative. Quantitative scoring or count means the more the better. So based on essentially TF or count. On the other end, I'm talking about qualitative. So this is a skipgrams. Match. On qualitative, I won't count how many times I see it, but rather how tight is the span, right? In a qualitative sense, I would much rather have the 3 or 4 words I ask together close, rather than having it say 4 occurrences, but they are loose everywhere in my, say, document. You know what I'm saying? So if I look for Virgil, Pablo, Northeastern University, Boston, 5 words, would I rather have a document that has those 5 words together, but only once? Or would I go for a document that has those multiple Virgils in Northeastern University and Boston, has each one of those words occurring like 7 times, but none of them is together? Which one's better? Right. But why? Okay, so that I went to the 5 gram. Because I give an example of 5 words, right? How about nuclear bomb? It's a bigram. Would you are a search engine right now, and somebody has nuclear bomb. Of course, you don't know the intention of the user. It'd be nice to know what the user wants to find out, but you only see the query, right? Nuclear bomb. And you have 2 documents. One contains only 1 time nuclear bomb, but it's tight next to each other. The other one contains 3 nuclears and 3 bombs, but they're not close together. They're always like in a distance of 10 words to each other. Which one's better? I don't know. Why? No, I really don't know. Because see, it all matters comes down to user intention. You are a search engine and you have to make a decision what to do. In terms of skipgram matching, this is always an issue. I get things that are tied together but rare, or things that are not tied but many. So how do I balance that? So that's the problem I'm dealing with now. I say in the case of most bigrams that are specific words like nuclear and bombs, my personal Virgil's intuition here is that I would go for a page that has rather counts, quantitative. I'd say a page that contains the word nuclear and bomb few times, even if they're not together, is probably more relevant to nuclear bombs than a page that mentioned only once nuclear bomb. I'm just making a guess here. Maybe that page mentioned nuclear bomb as a advertise or menu or something like that that's accidental, as opposed to a page that has a lot of nuclear bombs. My moral here is that what kind of skip-grams tend to be more quantitative in terms of matching versus what skip-gram tends to be more qualitative? For which these ones is not the count or the TF that matters for us, but rather the minimum span. We want them to be tight, to match tight. And my point is, if it's a long skip-gram, like 5 words, or a sentence, we probably match it qualitative, right? If somebody asks 5 words, you probably mean, I want to see those 5 words together. If somebody puts a bigram or even a trigram, they may be more like quantitative matching. Unigrams are definitely quantitative because there is no span in unigrams. Make sense? Okay, but how do we actually do it, okay? So there's a problem here, and there's some sort of mathematics behind it. How do we account for this thing? People have come up with a formula, some sort of amortized TF. Amortized, by the way, I made up this word. It's not really amortized. It's some soft TF. That says, I'm going to count all occurrences, but not as one. I'm going to count each occurrence according to how tight the match was. So I want to count some things like high because the match was very tight. And I want to count some things like not so high, but not 0 because the match was loose. So I think there's a formula that is a sum over all the S, it's, or K, I forgot. K is occurrence span. So K is the how long the span was for each occurrence. If I have 3 occurrences, this would be a sum of 3 terms, right? I think it's a lambda, that's a fixed thing, and then there is a S minus K divided by K. Something like that.
When you're talking about the span, are you actually referring to the window size?
Yes.
Okay.
So I said here span is the
Okay.
difference between the first and the last. You can subtract 1, you know, that's depending how you want to count. If you want to count from 2 to 5, typically that 2, 3, 4, 5, that's a 4, right? So it's not really 5 minus 2, it's 5 minus 2 plus 1. That's what I mean, the window size. Counted by words, not characters. Typically we count words. Some people do count characters in a very special settings like OCRs and translation. There's some settings in which the span is measured in characters. Tweets have certain, character limits and stuff like that. But for most cases, when we talk about spans, we talk about number of words. TF, everything is measured in words. We don't say otherwise. So this formula, it cannot be right? It might be K minus S. So this formula saying S, I think in here, so lambda is a constant, and S is the best possible span. Which we know what it is the number of words in the query, right? If I have 4 keywords, the best span you can get is 4. You can match 4 keywords in less than 4 terms, right? So that would be how many keywords we have. So how this formula works, if I get a very tight K equal with S, this is 0. If I get a larger K, that's more than that. I forgot the denominator if it's K or S, but it's one of those two. And this is a number that the best I get at 0, so this gotta be between 0 and 1, right? So I'm giving you a simplified version. This comes from a machine learning theory, a kernel designed for text. So if people took machine learning or data mining and you talk about kernels, kernels are designed for certain type of objects, depending on the feature representation of these objects. There is a kernel designed for text matching. It doesn't work that well. Like I said, in IR, things that have the fanciest theories are not the ones that work very well. But there is an entire theory about the string kernel, and it comes down to a formula like this. It counts all the matches, but the tight matches count. The tightest score I get for when I get the span tight, what's the score here for that occurrence? So this is 0, so I get 1. But for anything that's not tight, I'm going to get less than 1. What happens when this k, let's say it's s in here. Again, sorry, I can look in my notes for this formula. Let's say it's s. What happens when k is really large? So I see my occurrences, but it's spread into the whole chapter of the book. I do have my 5 words, but they really spread apart. This k is really big. What happens then? High value, but this is a number between 0 and 1, say 0.6. So how much do I count that occurrence? Very low, right? So this acts like if 0.6, S is 4 because I have 4 keywords, and K is 20. How much is 20 minus 4 divided by 4? 4. 0.6 a power 4? Like a 0.07 number. So that's small compared to an occurrence of 1, which happens when I see my skip gram matching type. So of course you play with those parameters a little bit, see what you need, but that's how you can account for multiple occurrences and account for like how tight they matched. Okay. I still have the problem of what happens if I'm missing one term. Right? If I do it this way, what happens if I miss one term? Well, how would that work in that algorithm that we talked about last time? What would happen if I get the list? What does it mean to say I'm not having a word at all in this document? There's an empty position list, right? There's an entire position list that has no positions in it. So for that kind of problem, I can't just simply run the algorithm, because if I don't have the position list, I will have only 2 lists of positions. I get tighter spans because it's easier to get 2 things together than 3, but then I'm completely missing the other word, right? So I can't do that. People have come up with, I think, as far as I know, I never run such a thing, but they come up with a way to say, I'm assuming the position of the missing term exists, but it's very far away. So if my document length is 500, I'm assuming the missing term is in position 2000 as a default value. So 4 times the length. That's a parameter, of course, that's being changed depending on what I want to do. But apart from mathematics, what happens in a quantitative setting? How do we want to treat missing term in a quantitative setting? What does TF-IDF and language models and all that try to do? They're all quantitative scoring functions. When you miss a term, what happens in homework 1 models when we miss a term?
You have like what plus 1. You add 1 if like this is missing, right?
We don't add 1. We have a default probability value for language models. That's smoothed probability. Or in vector space models, we add a 0, right? We say don't do nothing in there, add a 0. So quantitative models are trying to compensate missing a term with having more of the other terms. Right? Are we? If I don't have a term, but I have some of the other keywords a lot, I may actually compensate the score in a cumulative or quantitative sense. That makes sense if we want an approach that's towards that. What happens if I put a 5 gram? Northeastern University, Boston, blah, 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 blah. People who put a skip gram of 5 words, they probably mean I want to see all 5 of them. So in a qualitative sense, I think it's better to return a page that has those words that doesn't have all 5. Now it's back to the nearing the span question. So if I miss the term, one term, would I rather prefer a document that contains all 5 but spread around, not tight. Or I prefer one that contains 4 of them, very tight, but missing the 5th one. So, Virgil Pablo, Northeastern University, Boston. Suppose I miss Boston, but the other 4 are tight. Is that good? In the document? That seems reasonable. What if I miss Pablo? Virgin, Northeastern University, Boston. There are probably quite a few Virgils in here at this university, right? That's a great chance to not have the right Virgil that you're looking for. You know what I'm saying? Like, I think it may come down to some entity tagging, what the word that you're missing. Did you notice in Google when you type a query, you can find, sometimes give you results and cuts of word, like outlines and cuts of word? That's this case, I couldn't find that word. So if I could find documents called missing word 1 versus missing word 3, I found the other 4 words, but either missing that or missing that. I have to make a decision which missing word I can give up easily. So should I give up Boston or Pablo? Virgil Pablo, Northeastern University, Boston. If you have to choose one to give up for this kind of query, which word you can give up? Boston, because it's redundant. There's only one Northeastern University and it's in Boston. But Pablo's not redundant. There's probably 100 Virgils around here in this university, right? So that comes down to a little bit of NLP. You probably don't want to ignore a person's name, but you may ignore a location that's redundant to a building or campus or something like that. That's obviously where it is. I think those kind of issues are, even now, after so many years of basic AI, not solved completely. So I think the moral of this story is that when you go for qualitative matchings, you gotta ask yourself, what does it cost me to miss a word? When you go for quantitative matches, you don't worry because those accumulator scores, they're gonna accumulate whatever they find in those documents. If they misses a word, the TF-IDF or copy TF-IDF has a certain balance. How many occurrences of the first query term will compensate for missing the second query term? That's when you define that K and B in Okapi TF-IDF, the asymptote, that essentially says you need 5 occurrences of this word to compensate for missing 1, right? And that happens here naturally, but in here you have to make some hard decisions. If I don't see a word, if I keep going with this algorithm, Stephen Kenzel that I showed you last time, we're gonna get a 0. If a term does not appear, we're gonna get a crystal 0 for this. I mean, there's no span, so that's NA return. Okay. I don't think I have a clear answer for, if you want to implement this in the homework, what should you do? But this is what it comes down to. If you implement this formula, you cannot assign, so the only thing I can say for sure, you cannot measure K on fewer than S terms. That would be wrong. So say, if I miss 2 terms, I measure the span of the other 3. And if they're really tight, bingo, I'm good for that. That's not gonna work, right? We have to make some sort of default assumption about the missing query terms. Because you can get much better spans for 3 words out of 5 than you can get for 5. So again, we don't want to reward the documents that miss the terms by giving them short spans or tight spans because they miss the words. All right. So that's all I have to say about this. If you come up with some implementation of it, we should talk about it at office hours when you have it. I think it's going to work for some keywords much better than for others. How about pseudo-relevance feedback? This is a very powerful strategy that can improve your results a lot, and it doesn't require much effort, either intellectual or content-wise. So pseudo-relevance feedback. Run a query produce result. Result could be in the form that you are producing, this list of documents produced for a query. Fine. Then analyze result. I'm going to say result rank. So I mean a rank list of results. Analyze result for unusual. This is a keyword, unusual here. Rare terms at the top ranks. Unusual, it's up to you to define. What I mean here is I'm going to look through my result list at top K ranks, say top 10. I don't even know what the query was, okay? Let's say somebody put a query. I'm going to look at top 10 results. I already have those top 10 results because I run my system, either Elasticsearch or my own system. And I noticed the word China being much more frequent than China normally is. I can measure TTF of China, right? Like I know how frequent a word is. So China or Virgil or nuclear bomb, they're very specific words. They're rare, right? It's not like, you know, English constructs that can result accidentally in the word China. So I look for words that are normally rare, but in the top K results are not that rare. So by unusual, I mean a delta between regular frequency versus top K frequency. So I'm looking for words that normally I don't expect to see them that often, but in those top 10 or 20 results are very, much more frequent. I add those terms to the query. And then rerun. So maybe China was not part of my initial query. But I noticed China is a very unusual word for the top. It's much more frequent at the top than I expect normally to be, which tells me it's probably related to the relevant documents for this query, whatever the query was. So I'm adding this word or some other words like that to my query, and I rerun out that query including those words. This is pseudo-relevant feedback, because I don't actually have true relevance feedback. Nobody told me the top K documents are good. Suppose I run my system incorrectly and I get random documents at the top. I can look into those, but I'm not going to see anything good because my top ranked documents happen to be random. But if I believe my system does something meaningful, it's expected that the top documents to be, in principle, on average, more relevant than the bottom of the list, right? So whatever words appear much more frequently than usual in those top documents, I probably relate to my query somehow. This is a semantic matching, effectively. I don't know how they related, but people who wrote these documents about my query apparently put this word a lot in them for whatever reason. So I'm taking the word, add it to the query, and rerun. How will this help? Yes?
How many words can you add? I mean, do you have to add 1,000? Wouldn't you make your query even longer?
That's up to us, but I would say add 10.
From the first document?
From top K document. So I'm doing analysis on the top of the list. And I'm saying, I look at top 10, 20 documents. What's the most frequent words in here that otherwise are quite infrequent? So I get few words like that, maybe 10, maybe 15 words. Add them to the query. Now my query, instead of 3 words, maybe 10 words now, or 12 words. I rerun that query. I'm having in mind a quantitative match. So I'm assuming every one of these terms gets matched quantitatively based on counts and probabilities. I'm running my queries. Now my query, instead of 3 words, has 6 or 8 words, depending how many words I choose to add to it. why would this be a good thing? The documents that are at the top will obviously stay at the top because I pick words from those documents. It's only going to increase their scores.
But there might be documents where China is occurred with more number of occurrences, so that might come.
Right,
Which is-
documents
since you're
that
taking the
contain these words that I've added more, but the original query terms less. And somehow there is a relation, like a synonym or semantical relationship between them, and it would be hard to find otherwise, but because there's a relation between these terms on the top of my list and some other documents, I could pull those documents higher in my list now. Right? That would obviously be the case with a synonym. If I'm looking for a specific word, its synonyms might appear at the top of the list. So I'm taking the synonym, add it to my query, run the query. That way now I can pull documents that have the synonym but not the original query term. Make sense? Who's with me? Hands up. All right.
But will it always improve?
No, but most of the time it does.
Because what I was saying is, I mean, now you add a word China. So there might be documents which contain China more, and since you're using a quantitative model.
Right, so there is a guy, Rocchio, that studied this problem for his lifetime. Like that was his claim of fame, pseudo-relevance feedback. So that's the only thing he did. And he has this thing where you add words and subtract words. Just take some words of the query out, but I think people say that's crazy, so nobody did that. Nobody would take a user query and remove a word from it, right? But what they did, they keep the idea of adding whatever words with weights. So it's not really, the simple version is add the word China, rerun the query. The complicated version is add each word with a weight. The original query terms have the weight 1, and then when I add other words, I may add it with less weight than 1, so that when my new words that I've added come into, say, BM25 formula, they may contribute less or more depending on how I think of that as being important. If I happen to add a word that's not so rare, I don't want to count it a lot because that word may be too much. So there is a bunch of papers by this guy how to do this pseudo-relevance feedback. Now there is a version that's not pseudo. It's real relevance feedback. What do you think real means?
By human? By human?
By human what? So I'm still adding words that I see unusual. The difference is, where's the human coming into play? It's not up K anymore, it's what? A human looks at the list and picks the documents that are good. That way, even if my system did a bad job producing the results, I'm only going to add terms from documents that are certified to be good documents. Okay? What's between pseudo and real? I would like to get close to a human, but I don't want to ask people to judge documents for me. That's tough. On the other hand, top K may not be that good. It's completely automatic. Is there any sort of mixed feedback? Not exactly the feedback we want, but something that's already there.
Get the top K and then do the.
I'm Google now, so I don't want to talk the top K.
If you're Google, then you could just look at the ones that people click.
Exactly. It has been showing that click data is much more close to real feedback than to pseudo feedback. Clicks are not necessarily certifications of relevance. Like people click, I mean, even us, which are like presumably smart, we click at random on so many things, right? But it's no certification that if you click on a document, that's good. By good in here, by real feedback, I mean people who read the document and say, yeah, that's a good document for that query. Like you have in those Curl files. The Curl file used for tricky val, those are actually read by NSA analysts for that query and decided this is a good document. Clicks are not like that, but it has been shown that if you have enough data, clicks are very close to providing a good feedback as opposed to the top K, like completely automatic, especially for specific queries. The more specific those keywords are, like factual, or navigational, the easier it is to know that millions of people click on the same document, it's probably the right document. Right? So there is a real feedback. Use judge relevant instead of top K, and then there is click feedback. Use click docs instead. So this, of course, it's a good compromise in practice because it's very useful. It's not as good as human QA documents that people have really looked at, but it's close enough and it comes for free. If I'm Google, I can collect data for millions of people, doesn't cost me anything. Okay? So somebody asked me about this. I think you can try this. You can run any model. This is independent of the particular scoring function. Look at the top K documents. You can easily implement not the click feedback because you don't have clicks, but you can implement the real feedback and the pseudo feedback. How do you implement the pseudo feedback? You look at top 10, 20, do an analysis. Do I see any words that otherwise are rare, but they appear unusually high in here? Add those words, run the query. How do you implement the real feedback?
You
Read the curl file, the one they use for evaluation, right? That gives the answers. And pick from that curl file, you know exactly which documents are good. Look through those documents, pull up the query terms, the new terms that appear to be unusually frequent, add them to the query, rerun. And you can do this more than once. Probably has a very fast diminishing returns. But you can do this once and again, once again. This guy Rocchio did this systematically. Like, there's a whole loop in here of what happens after 3 iterations, 5 iterations, once. You have a question? No. Okay, so that's that. Let's go back to indexing. Our current enemy. You've seen the news today about who do we call enemies and foes and all that? Yeah, indexing is our enemy today. It's not really an enemy, but let's call it an enemy for today to follow the politics. So in indexing, we have an inverted file on hard drive. Right? So how do we say we organize that? Term, and then for the term, I have a doc ID and some count, and some positions array. If I keep to 2 positions, there's another doc and count and positions and so on and so forth. That is the inverted list for that term. I have another term, let's call it term 2, that also have counts, positions, so on and so forth. So that is my inverted file. And it comes to the catalog that says here term 1, here's the offset in bytes. Here's the length of the inverted list in bytes. And I may have other things. We mentioned these other things before. By other things, I mean things like what's the actual term if I keep IDs. I may store here that ID number 1 is that word. I may store things like TTF, whatever other things I want to store only once. So I have this catalog file here. Term 2, same offset, length. So this catalog is definitely in RAM, in the memory. The way I told you to do this, to simulate reality, is to parse only a partial set of documents and then be forced to write this file down. So I think the homework says 1,000 documents. You parse 1,000 documents, you have to write this down. Every time you write an inverted file, you have to have an associated catalog with it. Perhaps give it like inverted file 19, catalog 19, so you know which one goes with it. And now if you parse the next 1,000 documents, you will have, this is inverted file A, catalog A, and we have another one, which is inverted file B. And the catalog B. So this is also term DCP, term DCP, and this is the same term, say term 1 here. Offset, length, and things. So now that I have 2 of them, we have to have a merging procedure. In reality, we need other operations than merging. If you took an algorithms class, it's very similar to how you operate one of these fancy heaps. You need insertion, deletions, merges, all kinds of operations. For homework 2, we're only going to implement merging. So there's a question of, okay, how do I delete a document? I don't want it in my index anymore. Or update a document. But we're just going to do merging between 2 files. How do we do merging? This process is similar to merge sort, in conceptually speaking. We go, catalogs are both in memory. We go by one of the catalogs, read the term. As soon as I read the term, I pull up its inverted list from that file, associated file. Then I look into the other catalog, which is in memory. Is that term in there or not? If it's not, my output will be just the inverted list from the first file. If it is, I take the 2 inverted lists. I can read the 2 inverted lists in memory because I'm not reading the whole file. The point of these offsets is to tell me, go read into that file from there to there, and you just got back the inverted list. I merge the 2 inverted lists. The lazy people would just concatenate them. The serious people will actually look through the documents IDs to see what's happening in those lists. That's not graded, so we can just concatenate it. We write it down. The moment we write it down in the output inverted file, we immediately have to write the catalog entrance. The catalog entrance for the new file is not computed from the previous catalogs. We know the offset, we know the length, so we write it down. And you can do 2 at a time. Some people have tried to merge 3 or 4 or 5 files. The process is somewhat similar, although a little bit more involved, because I'm reading one from one catalog. Now I have 3 of them, say. I'm reading one from a catalog. What happens if I see it in another catalog? I have 2 lists to merge, right? If I see in all 3 catalogs, I have 3 lists to merge. That's okay. But how about the progression? So I think this is something maybe we didn't mention that hard last time. I'm reading the first term in here. If it's not in there, I'm just putting down the list. If it's in there, I'm merging the 2 lists. Then I do what?
You remove the term from the other catalog.
I remove it
Yeah.
from the other catalog. I mean, you could remove it, just make sure. I mean, removing stuff.
Because you're looping over only one of the catalogs. So
Right.
at the end of it, there might be terms which are there in the other catalog.
So you can do what he's saying. He's saying just my personality is to be very cautious. I don't like removing stuff. Okay, I'm not kidding. I actually think I have a good personality. Removing stuff will get you into trouble sooner or later. So I would rather flag them, okay, not remove them. But put the flag there. I've seen this guy. I use this guy. This guy is no good. Some sort of flag that will tell me, but complete removal is probably not that good. So I go to what he's saying. Go to term 1, term 2, term 3, and so on and so forth. And when I'm done with this catalog, am I really done? No, I may have some terms in the other catalog that I never went through, right? Because that catalog might have new terms. So what do I have to do now? I could go through this other catalog, not the ones I was iterating over, and look at my flags. In his case, he removed them, so for his, he's gonna look through the ones remaining in there and see, for the remaining ones, what do I have to do?
Type them on their file.
Take the inverted file. Do I have to merge it with anything? No, because they were not in the other catalog, just write it down. Okay, suppose now we implement this process differently. Suppose we implement it like merge sort. You guys remember merge sort? How does it work? It has two things that are already sorted. And how does it merge? It starts from the beginning, and it says if it's the same value or equal, what? Write both of them. That's the merge. And then if it's not equal, do one and move that pointer. Can we implement this idea? I'm not saying the first one that I said, run through a catalog and then check the other catalog, remaining ones, the ones that we didn't merge, just take them and put them down. Suppose we implement this merge sort idea exact. What would I need for those terms in the catalog? To be sorted by some criteria. Doesn't matter what criteria, as long as it's the same criteria in all catalogs, say alphabetical. Suppose they are sorted. Suppose this guy is sorted. How would I do the merging now? I put 2 pointers, one at the first term, one at the first term. What do I ask? Are they the same? If they are the same, merge the list, be done with both of them, so I advance both pointers. Now suppose they're not the same. This guy in lexical order is earlier or smaller. So there's a term here, they're not the same, my pointers. And this term is smaller. What do I do? Take the smaller one, take its inverted list, write it down, and advance the smaller pointer. Is that correct? Is it possible that if I have these pointers that point to different words, the smaller one that I'm thinking to move on with can be later on in this cat? No, that's the whole point of sorting, right? So if I'm at word algorithm in here, and this pointer is already at bomb, I'm saying algorithm cannot be found in here. The same like in merge sort. Hands up who's with me. I'm speaking a lot without writing anything or having any slides. That's the pedagogy 101. Don't do that. Don't speak a lot without stuff for people to see. Okay? I've been told that when I was 12 years old, giving like math lessons to kids. Sorry, but merge sort, come on, right? It's not that bad. So we can implement the merge sort idea by keeping those pointers up. If they're equal, merge. If not, just do the smallest one, copy the inverted list to the output file, and advance. Good. What if I have 3 lists, or I want to merge 3 inverted files with catalogs? Can I apply the merge sort idea? I have 3 pointers, right? Look at the smallest one of them. Actually, no, look at all of them. If they're all different, what do I do? Smallest one, copy the inverted list, advance. If they're 2 equal, the smallest ones are equal. It's algorithm, and bomb. Merge those 2, advance both of them, right? And if it's all 3, I merge all 3 and I advance all 3 of them. I think I can do that. Good. So I think that's pretty much the basic indexing. And you would have to retrieve stuff from here. The API that you use to pull an inverted list for merging is the same API. You only have one function that says, given a term and a catalog file, an inverted file, retrieve the inverted list. That's the same API that you would use to retrieve the TF values. You have to retrieve that into a data structure I would write only one function that puts that into whatever hash or matrix or a heap I want to use. And then for merging, I do something with that data structure. And for TF counts, I do something else with it. But once I retrieve that inverted list into the memory, I can process it for counts, document IDs, whatever I need. Good. So what we have to do in here is talk a little bit about encoding and compression. So we've been talking about how to manipulate those indexes, and we already mentioned that's a good idea for a lot of this stuff to contain integers. So most of the databases and indexing are designed that the internal stuff, it's all integer values. And there's dictionaries who can tell you what those integers correspond to if they're not integers. In fact, certainly computer representation, it's all integers. No matter what the original objects are, text, images, as an underlying representation, computer will use bits, right? So how do we encode integers? I mentioned a little bit last time about this v bytes and variable length. What was that idea? Let's just recap that idea. Fixed length was saying length is L, say 8. That's very simple. It says any symbol, every symbol on L bits. Easy to write, easy to read, because I know an integer may have 4 bytes, right? But I know exactly how many bits I have to read, and then it's only a matter of representation. If I use binary representation, I'll read it in binary. There was the variable length. That was a block of, I think the idea was a block of L things. They have a flag, and this is L minus 1 bits flag, right? So there might be another, this is where it ends, this block, and the other one is another flag, and L minus 1 bits, and so on and so forth. This flag, it's a very simple mechanism. This flag tells me if this is the last block I'm reading or not. So every time I see a 0 here, means this is not the last block. You have to keep reading at least one more. And every time I see 1 in the flag read, those bits are not used for anything other than those flags. It tells you this is where your symbol that you've been encoding ends. So this flag is 0 means not the last L bits, and 1 means last block of 8 bits. That means stop reading. After this block, this is a new symbol here. Whatever I was reading, I'm going to get those blocks that I have so far and then decode them according to my representation. If it's binary, I have to put those bits in binary and see what kind of, it's ASCII, I'm going to read those bits and see what kind of character I've got. I can encode any language, Asian language, and I look at the bits I have so far, what is that? Coding theory has a lot to do with encoding fixed length versus variable length, and prefix codes versus non-prefix codes. That is, if I'm reading something that makes sense so far, is it possible that this something could be a prefix of something else that makes sense? If I use these flags, that's possible, because the flags control when the reading ends. I see a 1, I stop. But if I don't have those flags, if something makes sense, I have to be able to say stop because it makes sense. And things that make sense cannot be prefixes of other things that make sense. That will allow me, if I have that property, as soon as something is a part of my dictionary, it's valid, I can stop because everything that's valid cannot be a prefix of some other thing that's valid. So as soon as I see something that checks the validity, I stop. I don't need those flag bits then. I can just use the content. That's too much for us today, but coding theory, especially transmission, people who study all these wireless networks and all that, in encoding, this is one of the basic problems that's being studied. How do I know to decode properly chunk of my transmission into things that make sense? Characters, letters, packages, whatever I have. How do I know when one ends and the other being, because in transmissions you get a stream of bits. So either you have control flags to know when to stop, or you have to look at the structure of bits and decide, this is done, I need to move on to the next one. Okay? And I'm going to show you one here that's more fancy. Let's see. I'm going to have to read something. Elias gamma encoding. So I'm looking at my value x. This is x, this is my value. And I'm putting it between powers of 2. I have to figure out which are the powers of 2. It's any integer value, it's bigger or equal to some power of 2 and smaller than some power of 2. So I'm going to write down 0, 0, 0, 0 n times. So this is unary representation, because I'm writing that n, the power of 2, literally as a bunch of zeros. And then I'm writing down, I think it's x minus 2 to the n. I'm not sure the exact value that's being written here, on n bits in binary. So, like I said with the encoding theory, to be valid, I have to be able to decode these things. I have to be able to know when to stop. Right? How do I know? Imagine I have a long stream of bits, and I want to read this value x. It's been encoded that way. How do I read the thing? I read 0, 0, 0, 0, 0. Where do I know that this first part, every part has two chunks? How do I know that this ends the first part, because this in here is guaranteed to be? That has to be 1 in here. So that's a question. Is this a 1 or not? But when it's a 1, I count how many zeros I've read, and I know n. So this n will tell me what? How many bits to read after that last 0. And now I read these bits. I know when to stop because I read exactly n bits. And now I can take this value, read it in binary, and make a value out of it. How do I know to get back to x from here? I add 2 to the n to it, right? I think the simpler version is to just keep the x here. Because I need to guarantee this 1 here. If I keep the x here, am I guaranteed to have a 1 here? How many bits takes x to write down? So if I have 2 to the n, let's say x is 35. Who's n? What's the power of 2 that's on the left side of x? 5. So who's n plus 1? 6. Right? So how would 30x equal 35 look like? 0, 0, 0, 0, 0, right? That's n equal 5. And then, how many bits do I need to write down 35? What's the 35 in binary? 1, 0, 0. This is the 32, right? And what else do I need to get to 35? This is 16, 8, 4, it's still 0, and then 1, 1. So I need to write down this thing. I need n plus 1 bits. And I need to guarantee that this value fits in n plus 1 bits, and I also need to guarantee that the first bit is a 1 to make sure I know when to stop the first phase, the zeros. Would it be efficient enough as a representation? How many total bits are here, roughly? How many bits are here? I use for this integer. 2n? Order. Like the order is 2n. Is order 2n is linear in n, right? Is that an efficient representation of x? Because if x is between those two powers, I think there's a theorem that says you can't use less than less order of n bits to write x without confusion, without writing multiple values to the same set of bits. Makes sense? So even though I use double the number of bits that's required theoretically, it's only linear increase. It's twice off, right? So it's not that bad. There is a trick to it, to write here the difference between x minus 2 to the n and still be able to read it. You still use roughly order of n bits, but the values can be a lot smaller because once I subtract the last power of 2, the difference might be a lot smaller than including the last power of 2. So this difference between x and 2 to the n, the minimum value is 0, and the maximum value, if x is all the way close to this other guy, what's x minus 2 to the n? So if x is almost 2 to the n plus 1, if I subtract it to the n, what do I get? So if x is 2 to the n plus 1, how much is x minus 2 to the n? 2. It's 2 to the n. Right? So that definitely fits within n or n plus 1 bits in here, because the maximum difference is that. Can be encoded easily, can be decoded easily. So this has been for a while used a lot. Google has created a revolution that was actually not well known in academia with their big table encodings and V-bytes that I talked about last time. It was not known because they did it internally and they didn't think it's a big deal. They just did it, make sense, you know, they keep working on it, progressing on it, and now only relatively late the academia people catch up and say, hey, these guys are doing something much more efficient than alias, gammas, and everything we knew. Because a lot of this stuff has been developed theoretically, but Google needed a solution that's very practical and scalable. So the big table, once you distribute them correctly over the file system, that distributed file system. By the way, Google has their own file system. Then those are much more efficient than this. Related to this issue right here, the MapReduce. We have a class now, MapReduce. Anybody took that class, MapReduce? It's actually called differently. It used to be called MapReduce. Now it's called parallelism. Right. Okay, that's a good class for people to want to be hands-on. If you want the kind of more like algorithm, research type of job or networking job, that's one thing. But if you want to work hands-on with those systems at IBM, Google, Microsoft, that's a very important class. It teaches you MapReduce, it teaches you Hadoop. It's really a hands-on how to get familiar with those distributed systems that are now used in practice. So MapReduce, it's a way to organize parallel distributed systems for situations like indexing, where I have the mappers. I have a slide about this, but I don't want to worry about MapReduce now. The mappers are essentially distributing the work. You can think in a distributed environment with many computers. The flow of data or information or requests comes in. Mappers are breaking this flow into parts, and they send it to certain machines. The machines, let's think about indexing. A mapper will take the stream of text and will break it into key value pairs, where key is usually the term. So you can think of a mapper or multiple mappers. If I have multiple strings of information, it reads those text that is coming to me, and every term gets sent to a certain machine or certain reducer that has a key, that term, and there's a values like documents, position, counts, whatever else I want to store about that, right? And how many times I've seen this term in this document. That gets sent to a particular machine. Now that machine may act as reducers for many terms, so a machine doesn't have to be computing only one term, but that machine may deal only with the following 7 terms. So every term that's Virgil in a document will be sent to that reducer. Reducer can do operations that's related per term. The reason of that is that reducer got all the information for that term. So all the it's like one of these inverted entrances. All the inverted entrances for the term Virgil went to that machine, and the reducer can compute any function you want for that term. You want the counts, you want the positions for that term, everything related with that term. You can ask that machine to give it to you. But other machines may not have that term unless it got duplicated. Everything is now, redundantly duplicated. If one machine goes down, a reducer, there is a duplicated reducer that has the same data, so it can act immediately instead of the one that went down. The advantage of this it's mostly to execute computation on the same machine where data is. That's very essential if you want to write scalable algorithms. Even whatever the algorithm's complication is, whether it's complicated or simple, or the problem with algorithms is that if the data is distributed in a network on many machines, and that has to happen at scale, right? If we have a lot of data, there's no way to put it on one computer. We want to distribute the computation somehow, if possible, in a way that whatever computation needs to access a chunk of data. In our case, computation is easy, right? We're going to ask for a TF list, or we're going to ask for positions. We want that to happen on the machine that has that information. In other words, we don't want to send a lot of data over the network. Right? If you have terabytes of data and an operation requires a machine calls for some mounted file system from a different machine that has to move half a terabyte of data, even if the computation is easy, the moving of the data will be very difficult. So all these operations for indexing are designed, the shards of Elasticsearch, you've seen that when you configure it, is designed so that the operation that gets access to data will happen, and the computation, if there's a computation like some function that needs to be computed, happens locally, and then only the result gets sent over the network. So MapReduce, it's incorrectly claimed by Google. This is not their idea. They say it is, but it's not. Many people have sued Google and won by saying that's not your idea. And one of these people is a professor at this university. You can look it up. Baklavsky, I think, is his name. He sued, I don't know who, I think Google, saying that's not actually your for copyright purposes. They claim it's theirs, but it's not theirs. They're the ones who indeed make it very popular and very useful for indexing. That is true. But the original MapReduce idea, to not move data over the network, to have the mappers map the data and the computation to the appropriate machine, reducers do the computation and just return the result back. That existed way before Google was invented. just not very used in practice because nobody had that much scale of data to really try that method at scale. So those are very powerful ideas. Hadoop has a lot of facilities for implementing MapReduce systems. However, some algorithms cannot be easily broken into mappers and reducers. A lot of machine learning algorithms, why Hadoop existed way before Spark, if you're familiar with, that now translate machine learning algorithms. Many machine learning algorithms are not readable easily in the framework of mappers and reducers. Indexing is, and search is, and all these accumulator functions like TF-IDFs, those are. But if you take gradient boosting, for example, machine learning algorithm, that's not easy to break into mappers and reducers. So people have come up with a different framework for doing so in a general, more machine learning sense. However, some algorithms are. So a lot of the simple algorithms could be easily implemented, distributed over a network for data without Spark. But if you want to work hands-on on a big company or a small company with data, you have to know about Spark and Hadoop and the basic operations. Even if you're very good at math and you know algorithms and all that, if you want to be a hands-on person that do a lot of engineering for data science company, you gotta have to do those systems because that's how everything is done today. Big companies will have their own systems. Like I said, Google has their own file system, their own implementation, but most small and medium companies will use Hadoop and Spark. Okay, at some point we're going to take a break, but not yet. You want the break now or later? Let's take another half an hour and then we take a break. So I want to talk about compression. I'm going to talk in general about compression, not specific for an index. Compression and encoding. So let's. I have two algorithms. The reason I say general is because those two algorithms are very useful to know, not just for AI, just in general. So one of them is Huffman codes. Huffman codes. Let me use this board first. Encoding Huffman. How many people have seen Huffman codes? Encoding. 1, 2, 3. Okay, let's do it quick then. Here's an example. I'm going to go by an example. We have symbols with frequencies in data. I'm going to just call these probabilities as proportion of how many times those appear. So I'm going to have an example. A here is 0.05. Right here. Let's see, I have 7 symbols here. A, 0.05. B, 0.05. C, 0.1. D, 0.2. E, 0.3. F, 0.2. And G, 0.1. Hopefully those things sum to 1 because they're proportions, right? Today. 1 plus 1, 2 plus 2, 4, 7, 10, right? There's some go. So the question I have those symbols in my data. And I want to encode them, aka transmit them over a wire to the other side. And I'm going to encode them with bits. So every one of these symbols must be a bunch of bits. I want to encode them in a way that the person on the other side of the channel can decode those signals. Now, we'll assume they have a dictionary. So once they have the proper bits representation, they will know what symbol that is. I don't have to transmit the dictionary. And what makes an encoding efficient? I think I mentioned this last time. Right, but how about how many symbols I have here? 7, right? How many? If I use a fixed length, how many bits do I need?
3.
Fixed length means every symbol gets the same number of bits. How many bits do I need?
4.
How many bits do I need? On 3 bits, how many things can I encode? How many possibilities are on 3 bits? 8. I need 3, right? I'm going to waste 1 because it's 8 possibilities, right? So I need 3 bits if I do fixed length. The problem with fixed length is that's not very efficient. Why? Things that are sent very frequently, what's the most frequent item? E. Would be better to be on less bits because it sends a lot. And since that are very rare, like A and B, would be nice to be on more bits because even though they're more bits, they not be sent that often. In fact, I can compute a measure of average code length if every symbol S has a code of S in bits. Then average code length is the sum for all symbols of the code of S. If I put bars like that, means what? Number of bits. Code, so for example, A as a symbol might be mapped into 001. B might be mapped into 010. C might be mapped into 011. D into 100, so on and so forth, right? So code of A is 001 in that mapping. Code of S in bars is how many bits are in there times what? The average code length has not just to do with how many bits are in each character. It has to do with frequency, right? So that's a probability of that symbol. Because how many times I'm going to send that code, it has to do with how frequent that symbol is in my data. A has a probability of 1 over 20, while E has a probability of 1 over 33, 3.3. So that's the average code length. This is not efficient for that reason. Frequent or rare, it sends the same number of bits all the time. So how do I produce a better system here? So Huffman have a greedy algorithm that turns out to be globally optimal. It's one of those examples in algorithm course on a greedy algorithm that achieves a globally optimal solution. It's rare for greedy algorithms to do so, but this one does. So Huffman code, they say combine the smallest 2 frequencies, right? So I combine the smallest 2 into, this is AB, because I combine them, and has the total probability 0.1, right? And then, again, now I replace both A and B with this AB. So I don't look at A and B anymore. Now, among the remaining one, which is A, B, and the rest, which is at the smallest 2, I'm going to pick A, B, and C. Right? So this combining those 2, I'm going to get A, B, C with total mass, total probability mass, 0.2. Okay? And now I have 0.2, 0.2, 0.3, 0.2, 0.1. The possible combinations are a 0.2 with a 0.1, right? So let's say I combine these 2 together into, this is FG with total mass 0.3. So now what do I have? 0.2, 0.2, 0.3, and 0.3. So which ones get combined? 0.2 and 0.2. This is now A, B, C, D. The mass, the probability mass is 0.4. So what are the remaining ones now? 0.4, 0.3, 0.3. So I combine 0.3 with 0.3 into, this is who? EFG, 0.6. And now I have those two combined into everything, A, B, C, D, E, F, G, total mass 1. This is a greedy procedure because at every moment I make a very local decision to combine the smallest one without looking at the total structure of the tree that I'm getting here. Now this is a tree, except it's on the side. Okay? So how do I assign our movement codes?
1 on 1.
Hmm?
0 and 1 on 1.
If I look this as a tree, everywhere a branch goes on the left side, that is for me up, it's a 0. If everywhere it goes on the right side, that is for me down, it's a 1. So I go from the root of the tree, and I say up is 0, down is 1. This is up 0, 1, 0, 1, 0, 1. This is a 1 here, right? This here is a 0, 1. 0, 1. So how do I now read the code for B? I look from the root and I look at the path, right? I say 0, 0, 0, 1. How about the code for E? 1, 0 from the root. Okay. Number 1 is this decodable. If I have a string now, suppose my stuff that I want to send is A, D, E, E, D, B. How is this getting coded? A is what? 0, 0, 0, 0, that's A. What else? B is 0, 0, 0, 1. So I'm going to put a little, so we know which are the symbols. But of course, I'm not sending any brackets over. I just send a stream of bits. What's E? 1, 0. So that's 1, 0, that's E. And then another E, that's 1, 0. D is 0, 1. And then B is again 0, 0, 0, 1. That's what I'm going to send. Now, how the person on the other side is going to decode this string? Yes.
Basically, I've written out the state machine that you're parsing, right? I mean, you start at the root, and then you always have exactly one path to follow for every bit, for every bit that you read. Right?
So, what I think you're saying is that you see this, you have the dictionary. The person on the other side have to have this dictionary. A corresponds to 0, 0, 0. E is 1 and 0, so on and so forth. So if you parse this string, this stream of bits, because it's a variable code length, you do not sure all the time. You have to be sure where to break it. If it be like here 3 bits for everybody, you break at 3 bits no matter what. In here is not 3 bits for everybody. You have to know where to break. How do you know to break after 4 zeros? Why not break after 3 zeros?
Because there's no prefix.
There is no valid code with 3 zeros. So this is a prefix-free code. Everything that's valid, like 4 zeros, it's not the prefix of another thing that is valid. When you see something valid, like 0, 0, 0, 0, you stop and break. Because why is that 3 Ys? How do we explain that phenomena, prefix-free code with a 3?
There's no cycle. Always
every code is a path from the root to a leaf. It's not to an intermediate node. None of these symbols are intermediary. So whatever path goes to an intermediary, that would be a prefix to a leaf. But the intermediary is not a symbol. The symbols are leaves. So no path to a leaf can be a prefix of another path to a leaf. That would mean this leaf is not a leaf. It's somewhere in between. This is a fundamental property of trees that you have to know. That in a tree, if I go from root to leaf, I get the path. And every prefix of that path, it's not to a leaf, it's to some intermediary node before a leaf. So that's how that gets broken into parts. Now the other property of codes is how efficient is this? In other words, if I measure my average code length, that is this thing here, would I get better than a fixed code representation? Better, I mean, on average over all possible strings that I'm sending, right? Of course, for some, if you pick a string by hand, it's going to have a lot of A and B's in it, and that's going to cause me to send 4 bits for each one of those. But the point is A and B should not be that frequent, right? So if I send a lot of data, a lot of text, or whatever I have, A and B have to be more rare than the others, and E must be the most frequent. Would this average be better for my code, the Huffman code, than for the fixed code? So this is the fixed code. What do you think?
Yes.
Certainly it's going to be better. But can anyone prove that this is the optimal code? In other words, it's going to achieve the minimum of any code that's valid, meaning decodable. I mean, I can encode everything with 1 bit. The problem is it's impossible to read on the other side. So any code that's either fixed or prefix free, so it is decodable, this has achieving the minimum average code length. So that's a theorem that we're not going to prove today, but if you're interested, I can discuss the proof with you. The way you do this proof is in 2 steps. First, you prove it for when these probabilities are inverse of powers of 2. Okay? For example, suppose my symbol probabilities are 1/2, 1/4, 1/16, 1/16, 1/16, 1/16. Would that sum to 1? Right. In this case, it's relatively easy to prove that this is optimal, because the probability that I have here are going to be exactly those numbers. And the code will be what? So the probabilities here are exactly the frequencies. But what will be the code associated in a Huffman way? If this probability is 1/16, how big that code is going to be? 4 bits, guaranteed. Try that out on a piece of paper. If this guy started with 1/16 probability, he's going to get 4 bits. What about somebody who has 1/4 probability? How many bits Huffman's going to give it? 2 bits. Right. How about somebody who has 1/2? That's 1 bit. So by doing first the probably 2 cases, we show that this is optimal in that case. And then we fit it between powers of 2. So we say this, and this example is not powers of 2. We say, okay, it's optimal up to some rounding error. I mean, it is optimal, but it cannot achieve a theoretical bound in here because the bits are the number of bits has to be an integer. So like in any encoding schema, I may have an extra possibility that I'm not using. In this one, it's easy to see I'm going to have a 3-bit possibility that I'm not using. In here, the same. There will be some possibilities not used because there's 7 symbols with some random probabilities. This is the case where cases like this, that's perfectly aligning to the theory. And the only one thing that I say here, the reason there's a bound, down limit of how low this average cone length can be, while it's still decodable on the other side, has to do with something called entropy. It is proven that the minimum that you can get to encode things, given the source probabilities, frequencies, is exactly this. You have to, of course, multiply with the probabilities here. This code length has to be 1 over the probability in size, log over the probability. So the theorem of minimum average code length, it says that has to be at least sum over the probabilities times log of 1 over the probability of S. And Hofmann achieves that, right? At least in the case of powers of 2, if this is 1 over 16, how much is log of 1 over 1 over 16? 4, right? 1 over 1 over 16 is 16. Log in base 2 is 4, right? So you can see that Hofmann achieves that optimality easily for the powers of 2. This is a theorem of encoding that you cannot get a code better than this. If you have a code better than this, there's going to be a problem decoding it on the other side. It has to lose some information. Like you can say, how come MP3s and JPEGs, I can compress it as much as I want, right? But they lose information. An MP3 and a JPEG doesn't have all the information that you found in the original picture or song. This is talking about lossless compression, that I can compress the data, but still recover everything out of it on the other side. So this is a bound that you can prove. It's not that hard to prove, the entropy bound. And then you can see that Hofmann, at least in that easier case, achieves that exact. Okay. Let's take a break now, and I'm going to keep talking about this in a little bit. One, two.
So I decided to read all the docs from 175, then tokenize, and then write it in the.
On one of these AP89 files.
Yeah. So I have like 365 files with all the tokens. So is that okay?
That's fine. Yeah.
That's fine.
Because we said 1,000 at a time, that's presumably 85 files. You're doing whatever it's in a file at a time.
Yeah.
It's
So
going
it's
to be.
always
Yeah.
less
You
than-
still have to merge them.
Yeah.
It doesn't have to be always less than 1,000. We're not going to look for that. But as long as you merge them correctly, it's fine.
Okay.
If the thing is the thing of 2, will be the work will be the same as the thing of 3.
What?
If the team is a person of 2, will the work will be the same as the team with 3 members?
I think more or less per person. I think that'll be fine. We'll have to. Yeah, I don't think it's going to be significant amounts of work. At some point in, I think, assignment 5, you're going to have a little interface, visual interface, where you can visualize a list of documents you search, and then in your index, the ones you crawl, and then you display the documents that you've seen. So we have some interfaces that you can adapt for your index, or you can write one. Most students wrote one. We thought of that as a team effort. So if you're just two, you have to come up with that visual out of two people instead of three. But in practice, what happened in any team, there was one guy designated, you write it, buddy. So I think 2 or 3 is just one of you gonna have to write that visual.
Okay.
It's not that complicated. Any Python interface, Java interface, and there's some already available online you can use.
Okay.
So that will be when I search for something, I want to search your index, the one with like all 100,000 documents, and I want an interface that displays the documents and has the ability for me to check relevant, no relevant, like a little box that says yes, no, and store that information.
Okay.
So I think it's fine, team of two.
Okay. And then about the pseudo reference, like so last assignment I implemented, but then I have to look for one term to another term, and it takes so long.
You don't look manually.
Oh yeah, I mean I trying to look for one term to another term to find which one is rare, which one is not.
That takes a long time.
Yeah, because like in a document there are many words, right? And then I have to look one that is not in the query.
But you go by what? By
Per word, one word, and then I.
where do you get the word from?
Oh, from the document, from the whole text.
The top document.
Yes, the top document. And it's like
Uh-huh.
top 10. And then I look.
But if you look for a term, you can get your inverted list from the index,
Okay.
and then you can immediately in that list know what documents and how many positions. You don't have to.
Yeah.
If you're reparsing the top
Yeah.
K documents
Yeah.
like word by word,
Yeah.
that's probably not.
Alright.
You have to get the term and say, okay, give me the inverted list. I'm looking which one of the documents are actually on top of my list.
Alright.
And so that's hook one. The other one that I have here, maybe there, is called Lempel zip, is the basis of zip compression algorithms, the ones that you use on a day-by-day basis. So Lempel zip. me. So let me start with a string of. I already processed my values into a string of bits, and I want to compress them. 0, 0, 1, 0, 1, 1, 0, 1, So this is the input. And there's several steps. This is the basic idea. The actual zip algorithm, when you say compress a file or zip a file, it's more complicated, but that's the basic idea. How do you think, what's the basic notion of compression in general? Without losing information. Like we say JPEGs lose information, but without losing information. How can I say, take a picture that's so many pixels by so many pixels, write it down in less space? What allows us to do that?
Finding patterns in the data and
Right.
compressing things.
What's the obvious pattern?
The number of same types of pixels, like.
Repetition, right? I have one pixel that's white, it's an entire rectangle that's white. Instead of writing for every pixel in the rectangle, the 3 values are RGB values, right? Instead I'm saying from this corner, that's 2 numbers, to this corner, that's another 2 numbers, it's all white. That way it will take a lot less space than writing every single pixel. So repetition. That's the same in text. If I repeat the same word or the same diagram many, many times, I could write it much more concise. I can say the words repeated 300 times. That's what this algorithm is trying to do, to say account for patterns and repetition. This, again, this is a simple version, toyish version. Okay, so step number 1, break into non prefixes. Okay, so 0, it's new, because I've just seen it. Now I'm here, right? I read 0, 1. I read the first 0. Have I seen this? 0? I've seen it, right?
Yeah.
So I'm going to read one more bit. 0, 1. Have I seen this? I'm reading from this input sequence. I'm 0, 1. I read those 2. Have I seen 0, 1 before? Break. Now I'm reading 0. Have I seen 0 before? Yes. I'm reading 1. Have I seen 0, 1 before?
Yes.
Okay, keep reading. 0, 1, 1. Have I seen 0, 1, 1 before? No. Break. Okay, where did I break? I break right here, right? So what am I reading next? 1. Have I seen 1 before? No. Break. Now I've seen 0. I've seen 0 before? 1. Yes. 0, 1, 0. No. Break. What's next? 0. I've seen 0 before? Yes. 1? Yes. I've seen it? So which one is this? Is this one?
Yeah.
Okay. How about 0, 1, 0? I'm reading the next one. I've seen it?
Yes.
Okay, keep reading. 1?
No.
Break. So I'm always breaking. As soon as I see something new, one more bit, every one of these patterns is something I've seen plus another bit that makes it new. Like this pattern to here, I've seen it before, but this pattern, including this one, I have not seen it before. Because if I have seen this before, I wouldn't have stopped reading. I would just keep reading one more bit, right? So what's next? This one is where? Is this one here? So next is 1. I've seen 1 before.
Yes.
How about 1, 1? Yes or no? Break. So this one here. I've seen 1. How about 1, 0?
but you didn't like show, you should be 0.
Which one should start with a 0?
Oh, this is the one that's in here, right? So this one here is the second one. And you're saying this is a 0?
Mhm.
Okay, 0, this 0, right? 1, I've seen that. How about 0, 1, 1?
Mhm.
I've seen it, so 0, 0, 1, is that like that? Okay, so I read up to here, now this 1 is 1 and 1, I've seen this, right? But I have to stop now because there's no complete story. But encode each block as a past reference back pointer, comma, and new bit. The reason I know this is possible is because every one of these patterns was something I've seen before and a new bit. So 0 is 0. This 0, 1, the 0 is the part I've seen before. Right? As a back pointer, it's kind of a delta. It's like, where have I seen it before? How many blocks back do I have to go? This 0, how many blocks back do I have to go to see it, to observe it? So this 0 here as a back pointer becomes a 1 because I have to go back 1 block. And this 1 is just a new bit. That gets written as it is. Then in here, the pattern 0, 1. How many blocks before I've seen it? And then the 1, it's a 1, right? This 1. How many blocks before I've seen this? 0. It's a new one. And then 1 is the new bit, right? How about in here? The pattern is 0, 0, 1 is the pattern I've seen before. So how many blocks back I've seen 0, 1? 3 blocks back. Because it's 1, 2, 3 is this one here. And then the new bit is 0, 0. How about this one? The pattern is 0, 1, 0. Where is that? 1 block before, comma, 1. 1, 1. The pattern is 1. So it's 1, 2, 3 before. 1. This in here, the pattern is 0, 1, 1. How many blocks before? Remember, I must have seen it before. That's why I kept reading bits. So how many blocks before I've seen this one? 5 blocks before. 1, 2, 3, 4, 5. It's right here. And then the new bit is 0. And then 1, 1. I've seen it before the whole thing. 1, 1 is 1, 2 before, right? And it does not have a new bit. It's just the end. It's not, does not say question mark, let's say end. Okay, last step. Encode back pointers in binary on certain number of bits. So I'm going to read each one of the back pointers and I'm going to write it down in binary. Obviously this is not binary. But for each back pointer, I'm going to use a certain number of bits, right? We all know in binary, the representation is unique, but I can add a bunch of zeros in front of the number if I want to, and that doesn't change the number. So how many bits I'm using to represent any one of these values it's depending on the order of the back pointer. So the certain comes to the rank or position of the back pointer. So here's how that's going to look like. The first one is 0. I'm going to still put these bars, but at the end we're going to pretend we don't see the bars because the bars not encoded into anything. Those are just visuals for us. When we send them over to the wire, there are no bars in between those symbols. So this 1 here is going to be represented on 1 bit. So this 1, there's another 1 here, right? So who's this 1? This is 1 bit representation for this one. So this bit here, this back pointer, which is the value 1, represented in binary on 1 bit, gives me the 1. Now the next one is, I have 1, 1. So the original sequence is, you know what, I think we should do this differently. Because I wrote it here, but I think it may be a lot easier to do what you guys do, to write it under this one. That way we can see a lot better. Yeah. So let's try to do this right under. So I'm still doing that. Encode back pointers into certain number of bits. 0 becomes 0. 1, it's 1 on 1 bit and 1. That's this one. This 1, this is 1 bit, and here this is 2 bits. So I have to use for this back pointer 2 bits, not 1 bit, which means what's the representation of this back pointer? 0. So I'm going to have 0, 1, 1 here. And then this one's also 2 bits. So the 0 will be 0, 0, and the 1. The 3 is also 2 bits. So what is true? 3 on 2 bits. Sorry, that's 3 bits. What is 3 on 3 bits? 0, 1, 1. And the next new bit is 0. Does it make sense? This is this thing in here. 0, 1, 1 corresponds to the 3, and 0 is the 0 bit. That's also 3 bits here, I think. So this will be, what is 1 on 3 bits? 0, 0, 1, right? And the last bit, which is the 1. This in here, it's also 3 bits. So that's going to be 0, 1, 1, 1. 5, that's 3 bits. So how much is 5 on 3 bits? 1, 0, 1, and the new bit 0. And this is 4 bits, I think. So 2 is what? 0, 0, 1, 0, and I need to have some sort of ending for the whole thing.
How did you decide how many bits?
That's exactly my question for you. How did I know 1 bit, 2 bits, 2 bits, 3 bits, 3 bits, 3 bits, 3 bits, 4 bits? What do you think this one's going to be? How many 4s do you think are going to be here? How many 4s? How many 3s do we have?
4.
How many 2s?
2.
So how many 4s we going to have?
8 4.
8 4s. So 1, 2, 3, 4, 5. And then how many 5s we going to have?
16.
16 5s. This pattern, how many 1, 2s, 3s, 4s, and 5s? That's fixed. Global, never changes. I'm giving you the simple version here. The actual zip that you run on your computer will say zip up this file for me. It's more complicated than that. But that's the idea. Now, why do we want to keep this fixed? First of all, it's always going to be possible if I keep this sequence. Is it possible to have some bit, some number here that doesn't fit in 4 bits? Is it possible to have a back pointer that simply does not fit in 4 bits? Or a back pointer here that doesn't fit in 5 bits? Or a back pointer here that doesn't fit in 6 bits? How many 6s are we going to have? 32. Is it possible that the back pointer value here, this might be a 17, right, or something, going back. It can go back anywhere, right? I'm allowing it to go back anywhere. Is it possible that this value is too big to fit to 6 bits? Why not?
You have a login, or you can fit to the end within those bits.
If this guy is between position, what's this position here? If this is 1 plus 2 plus 4 plus 8 plus 16, how much is that? How many positions are here? 31 up to 63. In position 31 to 63, the maximum possible back pointer, if you go all the way to the top, would be what? 63. 63 feet in 6 bits. Right? 6 bits. So by this schema, I will never have a back pointer that's too big to represent this number of bits. Now, of course, if I move here, the possible back pointer might be 80 something or 90 something, right? If I go all the way to the, it's possible that I see a 0 or a 1 all the way to the front. And then I will need more bits, right? The more I go into this section, I need 7 bits to go all the way to the top. And in this section, I need 8 bits to go all the way to the top. So this is enough bits to make sure I can write that down. Okay, that's good. How do we decode this? So what we get back is this sequence. Can I reverse all these steps? Can I put them in reverse? First of all, how do I break? Remember, the bars do not come with the string, just the bits. How do I know where to put the bar? The first bar will be after one symbol, after one bit character. The second bar will be 2. The third one, 3. The fourth one, 3. This one will be 4, 4, 4, 4, 5, 5, 5, 5, 8 times, right? Because I know these pointers are encoded in 3 bits, or 4 bits, or 5 bits. And I know to that, the new value is always 1 bit. So it's whatever the pointer encoding number of bits is. If I'm in rank, here, say I'm at 29, I know this is written on 5 bits, right? And then I need to read 1 more bit always for the new value. That's going to be 6 bits now. So I'm breaking out those. Now that I broke up, how do I read this? So I break up the sequence into parts. This 0 is the actual bit. How do I read 1, 1? I have to always make the last bit be a separate bit, and everything except the last bit, for example, this, it tells me what? Remember, that's a back pointer. So this tells me you have to read the value on the previous block, because the value of this the back pointer is 1. So it says take the previous value, and to that concatenate a 1 bit. So if I read this, is going to be 0. Now this 1 corresponds to 1, right? And then 1, but this is a back pointer. So this back pointer corresponds to the 0. Then 0, 1, it's a 1 and 1, right? right? This 1 here corresponds to the previous value because it's back pointed 1. Now 0, 0, 1 is what? 0, 1, because I'm encoding everything other than the last bit into decimal. 0 means don't go anywhere back. There's no back pointer here. Now 0, 1, 1 is a 3 and 0, but the 3 is really pointing back 3 positions, right? In here. 3 is not a value. It just tells me how many blocks do I need to go. This one here, it's 1, 1. So 1 points here. 0, 1, 1, that's another 3, 1. 3 points, 1, 2, 3 points in here. So on and so forth. And now, I can say, okay, this is 0. This one points to 8, so it must be 0, 1. This one points to 8, this must be 0, 1, 1. This one doesn't point anywhere, it's just the 1. This one is a 3, but what's 3 before it? It's 0, 1, right? So this has to be taken from here with a 0 next to it. It's the exact reverse operation that I had before. Hands up, who's with me? Okay? That's LimpleZip. It keeps track of the patterns as you've seen them, and it always refers to the new stuff as some same part plus a little bit of new stuff. There's many ways to play with this. The new stuff doesn't have to always be 1 bit. Right? I can modify this for the new stuff to be 2 bits if I want to. I just have to know how to control that operation. Also, do I really need to go all the way back? Is it possible that when I'm here, I mean, this is a theoretical value. This number of bits here, 6, ensures that even if my back pointer is all the way to the top of the list, I have enough bits to represent that back pointer. We said that already. But is it realistic that the back pointer, as I keep going, you ever compress a file that's like 100 megabytes? Right? That's a lot of symbols in there. So is it possible that by the time I need, say, 20 bits to write the back pointer, would I have a back pointer that goes all the way to the top? That's virtually impossible, right? Because to have a back pointer here means I have a 0, 1 type of sequence, but it's very likely that I've seen 0, 1 already, right? So in practice, the number of bits is not that big, but there is a mechanism to ensure that I can write the back pointers, and that is, but at some point, they do like they do in movies, keyframes. At some point, I start from the beginning. I don't want to allow back pointers that big, only for a theoretical possibility that I may have a back pointer that big. So maybe every once in a while start rewriting some sequences. I can also cache some of these very, very early frequent sequences. I may put them in a metadata somewhere where I can just point to them directly, not as a back pointer. So I can take any string of bits as an example here, and I can probably repeat this mechanism with characters or other things like that, right? With characters, because they add many characters, I would get much more possibilities on say 3 characters. The new stuff, the last character, is not just one possibility, 0 or 1, right? So there will be all kinds of possibilities, which means if my alphabet, instead of 2 symbols like in here, it's 28 symbols, like the letters, I may have to allow for longer back pointers, right? Because it's after 0 and 1 and 0, 1 and 1, 1, I've seen all the early stuff. But with the characters, even though I've seen A, B, and a bunch of other new characters, I still have possibilities to go all the way back to A, B. So in practice, I think this works faster with numerical data as the rate of compression. So how does it achieve compression? Suppose I have a repetition, a lot of, say, zeros, a lot of A's, something, one after the other. Right? So what happens if my symbols are 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. What's it going to do? Is it going to do anything good? So what's going to happen with those zeros? This 0 is going to be a back pointer to 0, and a 0, 0 now. So the blocks evolve how? This is one block, that's another block. The next block is 0, 0. The next block is going to be? The next block is going to be? So by the time I get a block that's very long, I can represent a long block just to the back pointer of 1 and the new symbol. So if this has the length, say 20, instead of writing 20 things down, the next one will be just a back reference of 1 plus the new symbol, that's a 0. So out of a block of 20 things, the next representative back reference would be 1, and then have a 0 associated with it. That's the new symbol, the next 0. So the block's increasing with every addition of a symbol. If they're repeating, if you're to calculate here how many symbols I'm using, the blocks are going to use 1, 2, 3, 1, 1, 1. So the back pointers will be 1, 1, 1, 1, the value of 1, right? It's just I'm going to have to every once in a while increase the number of bits if I'm allowing back pointers all the way to the beginning. So that's what the zip actually does. It partitions the data in such a way that this number of bits required for the back pointers is limited. It's never more than some constant. That way, any block that's repeating itself, it's never more than a constant number of bits for the back pointer plus one more bit additionally. And it's not one. There's like in B bytes, a combination of how many bits I can add. Maybe I can add 3 bits at a time, and I'm allowing that way for 8 possibilities of what's new. We can prove that lempel-zip has the same property as the Huffman codes. That minimum achievable average encoding length theoretically, asymptotically can be achieved with lempel-zip, but it needs some changes. Can't be just the toyish version that we did here. It needs some other changes, but there's a theoretical proof that if you have enough data and you do the right things with lempel-zip, it achieves the lowest possible bound. You can easily see that this is encodable, decodable. It doesn't lose any information, right? Everything I start with the input, I do my machinations, I go back to the decoding, I'm going to get back exactly the input. There's no compression loss in here. What's the main advantage of lempel-zip against Huffman?
You don't have to worry about the probability.
I don't have to worry about the probabilities. I think you mean like I don't have to measure it. I can just go in the sequence and work as I go. In Huffman, I would have to estimate or know these probabilities in advance. But that's not terrible. Most of the time you have data, I can estimate the probabilities in advance. That's an advantage. There's another advantage.
The representation is
Presentation of?
because there here you can represent with one back pointer and the last bit there you have to represent if there are 4.
I mean, theoretically, you still get the same lower bound. So in terms of the average code length, it may seem to you like there's a one back pointer instead of something, but Huffman has other advantages. Overall, on average, you get the same quality, which is the asymptote lower bound.
So this works on the stream of data as opposed to only on discrete symbols of data, right? Like this automatically creates the symbols as opposed to having to operate.
You're saying two things. One of them is the one I want, the other one is not. Both of them work on discrete alphabets.
Yeah, but I meant
So whatever it's in this data is still discrete, but the other thing that you mean is?
it's not, I guess, tokenized into, what am I trying to say?
Very close. In Huffman, when I'm done, for transmission to be decoded on the other side, what the guy on the other side must have?
The dictionary.
Dictionary, which in here is built in the data, right? You don't need a dictionary. It's included in the encoding. I'm not addressing at all security concerns. So I'm not saying from a point of view of security which one's better, so on and so forth. I'm just pointing out that this one would need a dictionary, while when you send a zip file, you usually don't send a dictionary with it to your, when you send the email, you just send a zip file. Okay. So I think that's enough for you to know in terms of compression. I'm not specifically talking about indexes. You can try to compress indexes that you have for AP89 data with encodings and compression. Use this alias gamma codes, try to compress them, so on and so forth. My experience is that both encoding and compression are a lot of headaches for small data. Like if you try this, you probably can kill a week of your life and get actually bigger indexes than the one in plain text, because you don't have enough data. But the exercise of implementing Lempel-Ziv of Hofmann codes might be worth the effort. I'm not exactly sure if, I don't think this homework requires compression, does it? Is that extra credit?
It's extra credit.
Okay. So if you want to do that, I'm willing to allow more days and time for this kind of, I mean, you don't even have to demo this. You can take your time to do it. I think it's definitely worth at least once in your computer science experience to implement the encoding compression mechanism. But I wouldn't be very excited about, oh, I'm going to shrink my index size from 80 megabytes to 60. Probably that's not going to happen. So then, I think what we have left, I think this is far more useful in a general sense. If you want to know about encoding and compression, not particular for text and indexing, these are the basic two schemas that are effectively used into most algorithms around data. You see, the other thing I have today here, which time we have? 36. I want to talk a little bit about something called power laws. We can probably talk about this next time. But that's another general item that is useful in general, not for indexing. So power laws are of the form y equal constant x to another power. So I have two constants. Or parameters. So as a function, this is y of x. We can say f of x. But we don't say f of x in here. We're just going to say y equal to that. So that's a power law. And I want to talk about two things that appear very naturally, one in general, one specific for text. So in general, I should say in nature, there is the following power law that's called Zipf law that says if you rank items by frequency, then you would observe that the rank times the frequency, rank of an item times frequency of an item is roughly a constant. So suppose we rank chess players by their, how many times they won the game. We'd observe that the first ones win 2 times more than the second one, which wins 1.5 more than the third one, in such a way that the ranking position by the number of wins times the wins, the frequency, it's roughly a constant value. Roughly, of course, that's not true all the time, but that's what people have observed. And you can replace chess with tennis players. Again, the number of wins, or with soccer, European Champions League winning games, so on and so forth. You'll notice that Real Madrid, which is the Champions League winner, actually wins about twice as much as the next one. Things like that. You can be observing these laws in biology, geography, all kinds of natural processes. There's a bunch of buses. The bus that comes the most frequent comes twice as frequent as the second one. The performance, grades, salaries, right? If you were to build this kind of graphs, the people who make the most money, they probably make double what the other, say, partition by classes makes, and triple times the next class, and so on and so forth. So that's a natural zip flow. How does this work for text? Why do I bring it up in here? Again, this is a natural law that people have observed it in nature. And this guy, I think, was at Harvard. Started as a linguist, but then he did other things. And he was preoccupied with this natural frequency of items. He thought text, the way we write words, has something to do with how brain is wired. He thought that whether you are English or Spanish or Chinese or Arab, the frequency that you use certain symbol or words has to follow this law in any language. The most used item or symbol or character or word is probably that much more frequent than the second one, and that much more frequent than the third one, and so on and so forth. So is this a power law in what sense? If I'm to write it mathematically, I'm going to say I can either use y for rank and x for frequency, or x for rank and y for frequency, either way. So I can express this as the rank is a times frequency at -1. Or frequency is a times the rank at -1. If I write it like that mathematically, who are my constants? Who's k? A. And who's c? -1. You'll be surprised how often this actually happens in text. In my slides, which I don't have time to put now, there's a bunch of words with frequencies and rankings. And while this is not happens all the time, it's actually pretty close. If you look at the top 20 or 30 or 50 words in English language, you rank them by the frequency, and then if you plot something like rank versus frequency, of course, at rank number 1 you get a high frequency, and as you go down to obtain this frequency is a times I at -1. So there's countless numbers of lists and observations about text, about concepts, about all kinds of other things that follow this kind of law. The other law that I want to show you has to do, that's more specific for text, it has to do with vocabulary. So the question posed in English is, as more text is observed, read, how vocabulary increases. So at some point I've seen new words, right? In the beginning, the rate of seeing new words is much higher than later on, because at some point I've seen so many words, chances are every word I'm reading is actually one that I've seen before. So it's kind of a diminishing return. But how, let's put here an equation. We're gonna say V is the vocabulary size. And N is the number of words that I've been reading so far. Then V is this is the power law. V is K times N at some beta. I'm giving it a notation. Of course, this is the same law as in here, so I could have used K and C. But this heap law, it's written usually in terms of these parameters. Mathematically, all this is equivalent in terms of K and C, just different. Instead of C, I use beta in there. And I have a table here that says K might be, for a lot of English text, between 20 to 100, and beta might be between 0.4 to 0.6. Well, of course, different readings, different texts might have different parameters. Now, of course, you could say, wait a minute, this is not going to happen exact, right? If I really rank all the items, I'm not going to get exact mathematical things. If I read a lot of words, I'm not going to, every time I break after every word, I'm not going to observe this law exact. Again, as a recap, this is saying when you read that many words, and there is a K and beta that will tell you how many unique words you've seen so far. Vocabulary means how many different words you've seen so far. How can we estimate from data K and beta here, or generally K and C, or generally in here we only have one parameter A, because the one is fixed -1. We used to have this exercise in the art class in one of the homeworks. Given a piece of text, you read one by one the words, and after, say, 10 words, 20 words, 30 words, 50 words, 1,000 words, 2,000 words, 5,000 words, after different n's, so you write here, n equal 10, n equal 200, n equal 3,000, n equal 50,000, so on and so forth. For each one of those, we'll have a certain V, right? Because I can stop reading at different chunks of text, and I know how many unique words I've seen at that point. So say I have a bunch of V's here. Now I call this a set of observations. How do I estimate the best K and beta to kind of fit a model like we say in machine learning, right? What will be the K and beta that mostly fit the data in here? I could look at it as a plot. I could say, okay, here's N, here's V. I know it increases almost linear in the beginning, because in the beginning, every new word is likely to be actually new. Every word I'm reading is a new one. So in the beginning it might be linear, but I know it's gonna kind of asymptote, right? Because at some point, words are not new anymore that often. Only rarely this is gonna increase. So if I observe these I have these 5 observations, that corresponds to like 5 different points, right? They're not, of course, linear. You can say there's a logarithm scale in there. And I could measure the V's at those points. I could measure the V's and say, I have 5 observations. These are my observations. Graphically speaking, estimating those 2 parameters, K and beta, has to do in this exponential family or power family, which curve passes the closest to these 5 points, right? By fitting a curve means I want a curve that's parameterized by K and beta, so I'm only allowing, the form is fixed, power law, and you can pick K and beta, such that it passes to these points as much as possible, right? As close as possible. That's what I want to do. How can I do this? For power law. So in general, again, I have y equal, what did I say there? K times x at c. But I have this for a bunch of observations. I have it for y1 and x1. I have a y2 and x2, y3, x3, and so on and so forth. So I want to say, given a bunch of observations, y and x, I want the best k and c to fit that data. How do I do that?
Can we start with something random and then change according to the graph?
No, like with derivatives. That would mean sort of take the derivatives and see where it goes. You can probably write some sort of gradient descent function that optimizes for k and c. What else can I do? I should take the log. That would make the problem a lot easier. So I keep these observations, but instead of keeping it this way, I transform it into log of y2. Right? And I keep x2, I think. I take the log only on this side, on the y side. I think you mean take the log of the formula. Right. So what is the log of the formula if I take the log? Log of y is log of k plus c times log of x. I think I should take the log of x too. Right? So I take the logs of my observations, and now I have one. I have a linear function here. I have a simple line. This is, in terms of the logs values, this is a simple line. Don't be tricked by this log of k. K is a constant, so log of k is also a constant. I have to estimate a simple line. That's a lot easier. Now a single line I can use regression, square, what is it? Least square fitting, many algorithms, very fast linear algebra that estimates those two parameters. This is some y equal b plus ax, right? I estimate those, and then for this one I have to reverse the log. If I estimate some value, k will be 2 at that power. Okay? So I'm assuming you guys know how to fit a line. My point here, estimating a power law is just like estimating a line if you take the logs. Alrighty. That's what we have for today. Good luck with indexing. Like before, demos will be a few days after the deadline. If you are coming Thursday with your